It's kind of crazy because we now make the basics about inductors and capacitors when typically it's the first thing you do. But in my experience, it seems that students sometimes forget the actual, I don't know, meaning or, I don't know, what they actually mean. They just consider the equations and they don't actually understand the physical principle. And in fact, it's good that we do it after Maxwell equations because we can interpret the physical phenomenon behind them. So I would start with capacitor. I don't know why, but it seems it's more natural.
Yeah, always a capacitor first.
Capacitor first, yeah. Because all the phenomena there are more, I think, more natural. I think the idea that you charge a capacitor is natural. When, on the contrary, if you talk about charging an inductor, people don't actually often see it so easily. So let's start with the capacitor. And so we have a capacitor. We define it with the value C. And thank you very much for closing the circuit, not for completing the line. How do we define the capacitance? What is the capacitance?
The capacitance is how much charge can be stored in the capacitor.
Not really, not precisely.
Not precisely?
How much charge can be stored is the charge. Correct? The charge that you can put in the capacitor is the charge.
And then, pardon me, and then it's also divided by the voltage in the capacitor.
So the capacitance is how much charge you get on your capacitor for unit of voltage, okay? So you have there 1 volt, it corresponds to some capacitance. You double the voltage, you have double the capacitance, okay? So Q equals CV. Which means that if you have a capacitor, and you have here the voltage, how is going to behave Q?
Oh, it's linear.
Linear, okay. Yes. So here we have our linear characteristic, okay? Are you sure it's linear?
According to the equation, it is.
Yeah, according to the equation, yes. Actually, we created this equation because we know that there is a linear relationship between Q and V, right?
Well, from your class, we learned that nothing is ever linear.
Oh, okay, no. Or if you go, this is another sentence I liked very much. If you look close enough, everything is linear.
Okay, yeah.
So if you go close, everything is linear. No, but besides that, of course, there is not an ideal capacitor, first of all.
Oh,
but
yes.
Let's talk about, generally speaking, let's keep in the ideal world. In fact, we created this equation because we know that there is a relationship between Q, between the charge and the voltage, which is linear. And then we say, okay, we know that there is a linear relationship, and we define the ratio, the slope, as C. Okay, C is the slope of this linear relationship. But let's watch the physics behind that. Do you remember what is the voltage?
The voltage is how much work is done to move a particle across an electric field.
Okay, so you have an electric field. You want to move this
charged particle.
The charge, okay. So in order to move it, there must be a force, okay?
Some work done.
And the force is the electric field. Remember, so let's say that you have a positive charge. It creates an electric field. Okay, so you have this electric field. Then here you put a negative charge, for instance, and it feels a force, okay? You remember this force is equal to, if this is the distance, okay? Okay, let's call it R. And this is Q2, okay? Okay, so you have this force.
Excuse me, D squared or R squared?
The electric field, So you put there a charge, you put there a charge, you feel a force, and the electric field is defined as this force that you feel divided by the charge, in this case Q2, that you put there to test the field. Okay? Take a charge, you put it there, you feel a force. The bigger is the charge, the bigger is the force, and therefore you define the electric field as how much force you get divided by the charge that you put there to test. Okay? So, therefore, this is going to be 1 over 4 pi epsilon 0.
Multiplied by 1 over Q2. Oh, yeah, yes. Cancel
So
it out.
you
Yes.
cancel out Q2, and you get, so the electric field is proportional to the charge, okay? So we can write it here. The electric field, or at least the amplitude of the electric field,
Yes.
is proportional to the charge. This is proportional, not equal, okay? Because the bigger is the charge that you have at the center, which creates the electric field, the bigger is the force, okay? So
Yes.
then the voltage will be the integral, let's say from point A to point B. Let's define 2 points here, A and B. And the voltage between these 2 points is the integral of the electric field between these 2 points over the line, okay? Over the line, if it's a conservative, in this case it's conservative electric field, so it doesn't matter the path, so you can go from A to B, and you have to create a work. In fact, the voltage is the work, as you say it, the work to move a charge, in this case, for instance, charge 2, from point 1 to point B. Okay? I have my charge here, Q2, let's say. I move it from here to here, and in this case, it's a negative work because if it's a negative charge, it will be attracted to, so it will release.
So you're absorbing energy because you're going towards it. You're not
well,
adding energy.
The system releases energy because it's going naturally in that direction. Okay.
Yes.
Well, actually, here it should be better. Like the voltage is like if you take the limit going to 0, like for the work. The infinitesimal work that you have to put to move that infinitesimal charge from point A to point B, okay? But if the voltage is the work divided by the charge, you know that here you have an electric field, which is the force divided by the charge, force times length, give you the work, okay? Fine, everything is hunky-dory. But, so, we know that E is proportional to Q. The voltage is proportional to the electric field. Okay. If you double here the charge in the center, you double the electric field, and therefore you double the work you have to require to go from point A to point B. Double the charge, double the electric field, and you know because the electric field is proportional to Q1, okay? So you double Q1, you double E, you double V, okay? So V will be proportional to E, okay? Which is proportional
to Q.
To Q, okay? So this tells you that between the voltage and the charge, there must be a linear relationship, okay? So now you see it here. So you have voltage and charge, which are in a linear relationship because of how you define the voltage, okay? Fine.
Okay.
So this is why we have this relationship. So Q equal CV. Let's take the derivative of this equation. Why not?
Okay.
So please try to derivate with respect of time this both right side and left hand side of this equation. Okay? Try to derivate. So you have the derivative of the charge. Okay. Okay, so in this case, you directly consider the capacitance as a constant, which is
Usually.
in this case, it's a constant. Let's say that nothing in the geometry or on the properties of the capacitor changes. So
Or temperature.
whatever. We consider
C constant.
the C as a constant. So when you derive CV, you take it out. Okay? Fine. So you say that the derivative of the charge in time, it's equal to capacitance times the derivative of the voltage. What is the derivative of the charge in time?
Flux. I think electric flux.
If you have some charge which changes in time, charge per unit of time is
Current.
current.
Current. Sorry.
So here you have the current is the
dV dt.
the derivative of the voltage in time times the capacitance, okay? Now this is a very, this is a very important equation, so we should
Yeah, that's the capacitor equation.
exactly. So if you want to know the relationship between the current and the voltage in a capacitor, so this is voltage current relationship in a capacitor, okay? The current is equal to the capacitance times the derivative of the voltage, okay?
Yes.
And it comes from the very same definition of the
charge.
of the charge as a relationship between the charge and the voltage, okay? Now, how can we see this equation? Well, still think to the capacitor, okay? So you inject some current, and then you develop some charge, okay? And because of the charge, you have an electric field, and because of the electric field, there will be
a voltage,
okay? What does it mean? It means that you have to pump some charge through using a current to obtain some voltage there.
Yes.
So, whenever you have, for instance, a current entering the capacitor, you will develop a voltage. It means that the voltage increases, okay?
Yes.
So, current goes in.
And voltage increases.
Voltage increases, okay? But if the voltage increases, it means that the derivative
is positive.
Will be positive, okay? So, maybe I'm not sure if it can be seen here, so let's,
nice.
Okay, maybe we can leave it there.
Yeah.
So, if you put some current in, you have a positive current, which means that you are creating a positive derivative of the voltage, which means that the voltage increases. On the contrary, if you are sucking out some current, it means
the voltage
will decrease because you take out the charges from the capacitor. So the voltage will change. In this case, it will change
negatively
in a negative way. So because it will decrease.
Yes.
So the derivative is negative. So if you don't remember this equation, you can either remember this one. Well, if you want, you can even start from the electric field anytime, but you can derive it. Or try to think it in this way. What happens if I put a current in a capacitor? The voltage increases, right? So I change the voltage.
You charge it.
And if I change the voltage, it means that there must be a derivative.
Yes, okay? There's a delta.
Okay, so you cause a change of voltage by giving a current.
Yes.
Okay, so the derivative must be there at the...
You can also maybe think of it as a capacitor resists changes in voltage.
Yes, we will get to that point later. Or
because
maybe
the resist change in voltage is delta V dt.
Okay, we could see it later, but let's see it now. what does it mean, this derivative? The derivative, let's say that you want, I was going to talk about that in a transient, but let's
we don't have to skip.
Let's talk about it now, if you want to talk about that.
And what about the c in that equation? The c would affect the slope of that derivative, wouldn't it?
Well, let's really go step by step. It's maybe better because then we will see the effect of the C in the transient. Okay. One thing which is interesting is the energy that the capacitor stores. But before getting to that, let's see what happens to this equation when we go on sine waves. Okay.
Okay.
Because that is most commonly what happens in an electric system. Okay. So let's say that we have this nice equation we derived. So we know that the current is the capacitance times the derivative of voltage in time.
Yes.
Let's say that we have a current which is sine wave, okay? So let's say that the current is going to be something like that. So the current as a function of time is amplitude, okay, peak value of the current, times sine of omega t, okay? Then the voltage will be, can you try to write it from that equation? If the current is the derivative of the voltage will be
the integral
of the current, which makes sense because it means.
Oh no, what am I doing?
Because the voltage is the result of how much current you pump in. Just write current, okay? Just write I of t. Let's not skip equation. Okay, so it means that we have to.
Never mind.
No. From 0 to t. Okay. So if I want the voltage plus the voltage of the capacitor at the time 0, but let's say that the capacitor is discharged, so we can remove that. Okay. So, but generally speaking, if you have a voltage with some capacitor, you put some current in, and the result of all this current that you put in, sum all together will give you the voltage. Okay, so that's the idea of the integral, that you integrate you sum up all this current that you put, all this charge that you put over time in this capacitor to build up a voltage. Okay. Okay, so you have 1 over c. The integral from 0 to t of
I
sine omega t, okay? dt. Okay, so this is the current, and so what is okay, so if you integrate the sine, you get minus cosine, and in this case, you have omega t. So you must get, okay, omega is, okay, you want to make step by step.
That's where that comes from.
Okay, so you know that if you have the derivative of
sine, it becomes cosine.
Sine omega t is omega sine, omega cosine omega t. So you always have this omega which gets out of the of the sine.
Just the identity basically.
So
or rule.
It's like minus
1 over C.
1 over
C
omega C
Yes.
cosine
Omega T.
Can you try it here?
Okay.
Fair enough.
Okay.
Just put here -1. So it's minus cosine. No.
Right. So this is 0 or 2 pi, and that's pi over 2. Okay, so, oh, this is time.
This is time domain.
This is time.
Just define, draw a minus cosine in this. Yep. Minus cosine, not minus sine. Cosine, you remember, come on. Okay. Correct. You can stop there. You don't need to continue for. Okay. So this is minus cosine. So this is going to be. Okay. Maybe let's use another color.
Different color. Let's make it red because it's current.
Because
no, this is voltage. This is voltage.
Oh, that's voltage. Okay.
But it was nice with the dots, eh?
It was nice. Yes.
It's my interpolation.
Okay. So your voltage.
Yeah, and the amplitudes wouldn't be the same because
no, it's not. This is
that should be current.
Well, this is the current. Okay. Where
I got it.
Okay. Here. Now.
So it might be greater actually.
They are talking about different units, so you cannot compare volts and amperes. How can you say that the voltage is bigger than an ampere?
Yeah, you're right.
You're right. Comparing.
But the amplitudes wouldn't be the same.
Oh, generally speaking, you have some ampere. Yeah, you have two different scales. So you have amperes and you have volts. Okay.
Yeah.
Now, does this suggest you anything?
Oh, that's 2 pi f.
Yeah, but 2 pi fc is what? 1 over 2 pi fc.
Oh, it's the reactance.
It's the reactance also. That
yeah.
Because here you have a voltage which is equal to a current divided by J omega. If you
that's
use
impedance.
The omega C, okay?
That's impedance. Oh no, that's okay. That's voltage.
That's impedance, and this is the reactance.
Yeah, I'm sorry, I'm retarded.
So you know that here you see that if you go to phasors, what happens? Here you have
it's lagging.
Current,
yeah,
which is horizontal, because at time 0 the amplitude is 0. Okay.
Yeah.
So here, if you have your real and imaginary axis, this phasor now I is here because at time 0
we had 0.
We had 0, so it's vertical component of this is 0.
It's real.
The voltage.
It starts at negative. Yeah.
Is here.
Yes.
Because at 0 time the voltage is negative. Okay.
Yes.
So this is the diagram. So you have J because you have pi half degree. Okay. And omega C because it comes from this, okay?
Yes.
So the fact that you have sine transformed into cosine gives you that J, which means that the sine becomes a cosine, okay?
Yes.
Okay,
yes.
so the fact that there is a J means that it's shifted by 90 degrees, by pi half.
But the fact that the J is in the denominator makes it negative pi over 2. So it makes it minus 90 degrees.
Yeah, of course. If it was J omega, then we will say later J omega L, it's
positive.
Shifted before.
But
if it's 1 over J omega C, it's going down. Okay.
So can we just do this quickly? If it's that's correct, right?
Okay.
And then
but you know that minus J is 1 over J. Okay.
Yes, yeah, that's how we brought the j up and it became minus sign. So now, how do we express this in terms of a scalar form? Not scalar? Excuse me. In polar form. In polar form, where you have your magnitude and your angle, it would be.
It's just an impedance times j omega the angle. In this case, j omega minus pi alpha.
I think it would be like this.
Okay, or you can simply say, if you have a complex number, remember, complex number, you can use the Euler formula.
Yes.
That you have the amplitude, you have real plus imaginary plus j imaginary part, or you can say that you have the amplitude times e to the j angle, okay?
Yes, yes.
So if you have a complex number, let's say any complex number, let's call it, give me a strange letter.
J?
No, J, no, because we use it for the imaginary unit.
I don't know, alpha?
Alpha, no.
Gamma?
Latin letter.
I don't know that.
One Latin letter, like M. Fuck.
Oh, okay.
Is alpha plus J beta. Okay.
Yes.
Then you know that the amplitude is the square root of alpha square plus beta
Pythagoras.
square. But you can use also like M as the amplitude times E J angle. Okay.
Yes, yes.
Where
the angle,
let's call it phi. Okay, so this is angle, so it's alpha, beta. So this is the amplitude of
that's
the angle,
Pythagoras.
and this is phi, okay.
And then phi will equal arctan.
Arctang of beta over.
Okay, let's not do beta, let's do imaginary over real.
Okay.
And then, okay, let's just write it. And then the magnitude of m is equal to the real squared plus the imaginary squared rooted.
Out of curiosity, does it? I was wondering why you wanted it in polar form. Do you feel more comfortable?
Yeah.
Really?
Seeing it like this is amazing because if you divide it, you can just minus them.
Okay.
If you multiply it, you can add them.
I just felt more comfortable with the real plus imaginary part, not the polar form. Like,
But if you're doing it like this, it's tedious because if you are adding these, you can't add them.
Okay,
you have to convert them back to this.
Like
add them and then convert them back to that.
I don't know. I always found more. Well, never mind. Everybody has its own favorite. Anyhow, here we have just the imaginary part, so who cares?
So that's where the negative comes from.
Yeah. So the negative is because we have a current, which is a sine. Then you take the integral, it becomes minus cosine, which means that if you have a sine, you get minus cosine. You have to have a shift in the angle of 90 degrees negative back.
Yeah.
Okay? Now, this is equations, but what does it mean from the physical point of view? Here you have a current, which is positive, right? And what happens? It happens that when you have a positive current in your capacitor, remember the equation here. Positive current means that you are building up the voltage. You increase the voltage. You put some current in, you put some charges, and the voltage increases. And that's exactly what you see here in this equation, because if you watch carefully, here you have a current which is positive. And during the time the current is positive, the voltage is increasing. Increasing. But it's not a matter of sign. Here is negative, here is positive, okay? So, let's draw again. This is the current, correct?
Yeah.
And
now
I have the voltage here, so. So this is our voltage, okay? Okay, the same graph that I had.
Yeah.
Now, we can see two different moments when the current goes in and when the current goes out, okay? So let's consider the first case, yellow. The yellow case is when the current goes in.
When you're charging it.
Exactly. So in this case, we know that if the current is positive, then you are pumping inside charges, so you increase the voltage. And that's exactly what happens here, okay? Look here, we start from this value of the voltage, and the voltage just increases. So derivative of the voltage
is positive
in time is positive, which means that it goes up.
Oh, wow, okay.
Until here. Until here when the current becomes negative.
Yes.
And the moment the current becomes negative, the voltage goes down.
Because now the capacitor is feeding the current.
The capacitor is giving away the charge. The charge.
And that reduces the voltage.
The voltage is produced by the charge itself, that it's inside.
Yeah. So because it's releasing charge, the voltage is decreasing.
The voltage drops down. So here the current goes out. Okay. The current goes out, and we know that now the current is negative. It means that the derivative must be negative.
Yes.
And that's exactly what happens here. In this case, the current is negative. And if the current is negative, the derivative of the voltage
is negative.
Which means that the voltage
is
decreasing. And that's exactly what happens in this period. The voltage here is maximum, and for all the time the current is negative, the voltage goes down, decreases, okay? So this is, again, the reason why you have the current, and then when the current is positive, the voltage goes up, and when the current is negative, the voltage goes down.
Here's a question though. If, let's say we just have a capacitor that's charging, you wouldn't measure a negative voltage on it. It would be zero. If you have a capacitor and it's in steady state, and it's at steady state at zero, right? So there's no charge in the capacitor.
So you have a capacitor.
And we start charging it.
Start charging, okay.
Okay. At T0,
the voltage is zero.
Yeah. Why is it? So would we start actually here in real life? Because this wouldn't exist.
Of course. Then you start. Yeah. Let's say that's a transient. That's what we are gonna see later.
Okay.
Okay. In a transient, you have. Let's say that you start with a capacitor which is gonna be zero. Okay. And then you inject some current. The voltage cannot change instantaneously, but it will change smoothly because you have the derivative. But the current, yes. Nothing prevents you to change instantaneously the current and give, from at the time zero, a current to the capacitor. Okay? So you start with a voltage which is zero and with a current which will be given by the condition of the circuit. Then we will see an example later.
Okay.
Another way to physically see this phenomenon is just think to a balloon. You know, the balloon of the party. Happy birthday. Okay. You know, you pump up the balloon and just think at the current as the stream of air that you blow in the balloon, okay? So what do you have? First, you blow the stream of air, and as a result, you get a tension at the balloon, okay?
You get pressure.
You give pressure there where you hold it tight.
Yes.
So that's the same thing. First, you give a current, okay? So you blow in the balloon, and then as a result of that, you get the voltage, which is the tension that you have there at the balloon, okay? So that's why first you have the current, and later you get the voltage.
Yes.
Okay, just think thinking
Yes.
like that.
Yes.
That's the same. That's the same thing. Okay. There is one thing which is kind of misleading here. I think very often is misunderstood. There could be the idea that when the current is positive, then the power is positive. Because we say we charge the capacitor. Okay.
Yeah, but it's reactive power.
Okay, yes, the capacitor doesn't dissipate any energy. It's just power which is received by and stored
This
there.
charge is stored power.
But, no, what I wanted to say, okay.
Stored power, that's a weird...
You might think that, for instance, in this first quarter of period, okay, in this quarter of period, you have positive power of the capacitor, because you say, I'm charging the capacitor. Okay, so the idea that, okay, I put some current in, therefore I'm charging the capacitor, so I'm giving power to the capacitor. But that's not true. Do you see it? First of all, is it confusing? If it's confusing, it's okay, because then we are going to fix it. How do you define the power in any electric port? Let's say that you have
VI squared. Right?
Power. Okay, let's start from the definition of power. What is a power?
It's how much work is being done over time.
Okay, so the voltage is the work.
The work done over distance.
The work done to move.
Oh, pardon me. The work done to move a charged particle.
Okay, so let's say that the voltage between these 2 points, A and B, is the work you have to put to a charge to move the charge from point A to B divided by
the charge
of
itself.
The field. Okay, so let's say that you you want to move a charge from here to here, you have to put some work. If the charge is double, you have to put double work. Okay, fair enough. What happens if we take the voltage and you multiply times the current? You get this elementary work over the charge, and the current is?
The current is flow of electrons in a surface area.
So flow of charge.
So it's
in
dq
time,
over dA.
dq over the time. Is the current, remember, is how much charge flows per unit of time.
Where did the area go?
No, in a defined area. Like let's say that you have to move the charges from point A to B through a wire, okay? So the wire is connected between point A and point B. And inside this wire, there are the charges which flow, okay?
Okay.
So this is...
Q's cancel out. And we have...
So if you have 2 points of any electric circuit, okay, and you want the voltage between these 2 points, the voltage is the work that you have to take to move the charges from the point A to point B. And the current will be the amount of these charges which are going through the wire from point A to point B, okay? In a unit of time.
Yes. So it's work over time, which is power.
Which is power. Bim, 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 bim. Okay? So, if you want, you can say that, let's put it here. The elementary work will be the voltage times the elementary time, okay?
Oh, no, there needs to be current.
Sorry? No.
The work is...
So this is the power, okay?
So, yeah, it needs to be VI dt. Because this goes down here. And if you want that,
okay.
that goes there.
No,
so
wait.
dW is VI dt. Or are we missing something?
This is the power. Okay, sorry. I'm maybe confused. So if you want the elementary work, Let's put it this way. This is the power, okay? The power is the elementary work over time, okay? If I want the work, okay, elementary work, I have to take the power in time, okay?
Yes.
Which is V I.
Okay, there we go.
Okay?
Yeah.
So you have the elementary work, which is VI dt, okay? Okay, so it means that if you give some power in, if you give some energy in, it means that you have voltage times current, which is positive, okay? And let's draw again the current. And this is, again.
Yeah, get those phases. Nice.
Okay? So here you have, my drawing skills are not so good, but
That's good.
this is the voltage, okay?
So now we should times those.
Exactly. So here you have positive,
Negative.
negative. So the power
negative.
is. Can you draw it? Can I try? I should make a lecture only for that. How to make dotted lines. Okay.
Okay, wait, so what am I going to draw here? I'm going to draw the...
Times voltage and current.
Okay, well this is going to be negative.
Okay, and here the value is?
0.
0, because you have 0 current times voltage.
So here, right?
And here is going to be also 0. Okay?
And then positive.
Mm-hmm.
And then negative.
Mm-hmm.
And then negative?
No. Negative times negative is?
Positive.
Mm.
Yeah.
Okay.
Sorry.
So here
and
you
this
have...
is P. This is V.
This is I. So this is negative, positive, negative.
Sorry, I'm retarded.
Positive. That's fine.
Yeah.
Fine. So this is... So what happens, in fact, in the first part? It's true that we are giving a current in. So you might be led to think that we are giving power to the capacitor, okay? But the voltage is negative, okay? So if you watch from this side, the current enters here, but goes out here. So what is that? It's simply a generator, a source of power. So that's why, even in the current, if you watch it here, you say, current goes in, so I'm
charging.
I'm giving power to the capacitor. But the opposite is true, because the voltage is opposite. Okay, so then if you watch here, the current goes out, and you have basically the same directions for the arrows of a source of power. So the power goes in this direction.
It's a delayed source.
What does it mean, delayed?
Well, if you push in 1 amp, you're not going to immediately get 1 amp out.
Of course, you got it later.
Okay, let's not go. Let's not go.
No, but that's the point. Maybe it's better to... You see, you don't have to think in terms of current. Oops.
Come
Can you see
closer.
me? Okay.
No, you can sit down, just come closer.
Okay. you cannot
That's it.
you cannot think about of current, or maybe you can, but if you think only about the current, it's always going to be misleading, because you have to think about the power. Okay, think about the energy, and therefore the current. So how much work, how much energy gets in or out. If you think about the current, you see there are these 2 points, these 2 moments where here you have current, it's still positive. You're still giving current, okay? So the current is going inside the capacitor. But here,
voltage is negative.
The voltage is negative, so the energy gets out. Here, the energy is positive. The power is positive, so the energy gets in. Even if the current, like here and here, you have the same value of current, right? Correct? But here, you have negative voltage. Here, you have positive voltage, so here you have positive power, negative power. So the current itself doesn't say if you are giving or receiving. Check always the power, because that's the power which tells you if you are giving or receiving energy, okay?
And if we integrate the power, we would get 0.
Of course, if you integrate over in total number of... So this, of period, you get 0. This tells you that the capacitor doesn't dissipate any energy, okay? It's just a storage. You can put energy in, and you can take it out.
Yeah.
But the energy is not going anywhere else if it's an ideal capacitor. So maybe we can talk about the energy. Okay? Maybe let's watch how much energy. So here, if you integrate, of course, you get 0. But at some point here, you have taken out some energy. Here, you're giving out some energy. So let's watch how much energy we can put in a capacitor. Okay? So let's start from this. Okay? I like very much this equation here. So we know that the voltage is the elementary work to move the charge, okay, between these 2 points. Oh, whoop. And let's watch again this characteristic that we have here, okay? QV, you remember. That's the characteristic of the capacitor, and you know that
it's linear.
It's linear, okay? Let's rearrange this equation, okay?
Okay.
And let's say that the elementary work...
Oh, is V dq.
V dq, okay? So this is the elementary work that you have to make to move this elementary charge, dq, between these 2 points when there is some voltage, okay? And maybe we can see it here. Like, let's say that we have this point here, we have some voltage, okay? Let's draw it better. Okay. So here there is the voltage V, okay? And dq is a very, very narrow slice of charge, okay? So we can see it like
infinitesimally small slice.
Infinitesimal, correct? So let's say that here we have a dq of charge, okay? Now what happens if I want the whole energy which goes into the capacitor when you move the charge from 0 to Q, okay?
We're going to integrate it.
We're going to integrate, okay. Which means that you have to take...
The integral...
Well, let's again watch at the physics. You start from here, okay?
Mm-hmm.
So this is your start. There is zero charge in the capacitor, is this charge. So the voltage is 0 because we know that Q equal CV, okay? So 0 charge, 0 voltage, discharged. And we want to arrive to here, okay? Where you have Q charge. We put the current, and by putting the charge,
We increase the voltage.
we increase the voltage, okay? Until we arrive to this point here, to the total voltage, to the final, let's say this is
VF.
end or VF, okay? That's a final pain.
Broke the sacred chalk.
Yes.
And then there will be VS at the first one.
So this is F. VS is 0.
No, but you said we're going from this one.
No. This is just an example.
Okay, so we're going from
So
S to VF.
We start from here to here. We have to integrate for all these slices the elementary work done, which at each point is dq times v.
Yeah.
Okay? So we need the total work, let's say the total energy that you put inside.
It's just going to be the integral of v dq.
It will be the integral of v dq when the charge that we put in the
So 0 to v.
0 to q.
Oh, to q, yes.
Because you increase the charge, you put the charge inside, you increase the charge of the capacitor from 0 to q, and for each moment you have to integrate the voltage time dq, which is the elementary work, okay? But the voltage is not a constant, okay?
No, it's changing.
It's changing. It's a function of Q.
Yeah.
Okay? So the voltage, in this case, will be Q, the Q that you have to integrate.
Q over
so
C.
Let's call it minor, small case Q, over C, okay? So it will be the integral of U.
All right.
What?
Q over C.
Q over C.
dq.
dq, okay?
So then W total
So get
is going to be 1 over C Q squared over half.
Okay, over 2.
Times 0.5. So that's going to be half.
Okay. Yes, I think it can be visible, yeah, if you move.
No, but you need to...
To move the chair?
That's where the chair should be.
I can even remove it, put it here.
Yeah, but if you need to... okay.
So, here you have 1 over half Q squared.
Yeah.
Q squared minus 0, so Q squared. Okay. So, now you know that Q is CV, okay? So you can even write it as
CV
1 over
squared.
Half C
times CV squared.
CV squared. So 1C cancels. So you have 1
half.
over C CV squared. Okay, that's the same thing. Okay?
Yes.
Okay, because
Yeah,
this is C squared.
Yeah.
1C is cancelled by the C denominator. So you have 1 over 2 CV. Okay, whatever. So this is the energy that you put in. And here you see...
Wow.
What, why?
That's a good connection.
Okay. So if you move from a point here where the charge is 0 to a point here where the charge is whatever is the value, let's call it this small case Q. Now the energy will be all of this, okay? And that tells you that, oh, well, you can even calculate because it's here is the area of the triangle. So you have QV 1 over half. So again, you can even calculate it without making the integral. You watch it from the figure, okay? This tells you that if you start from here, so this is the initial, this is the final point, you cannot move from here to here in 0 time. Okay? Why? Because you would need to move all this energy in the capacitor in 0 time. But that would be impossible. You need some time to transfer the energy, okay? The energy doesn't just transfer in 0 time.
That's when things blow up.
Well, yeah, definitely yes. If you try to... Why it blows up? Well, because let's see what it means that I cannot go from here to here in 0 time. I cannot do it because otherwise I should transfer this red energy, this energy corresponding to the red area to the capacitor in 0 time. But this means that I cannot move from the initial to the final point where I have a different voltage in 0 time. So the voltage cannot change as a step. In a capacitor, I cannot have a step of voltage, okay? If this is the voltage and time, I cannot have the step of voltage. Because a step of voltage means that I change the energy in 0 time. Here, look at the energy. How much energy we have? 1/2 CV squared, okay? So if I change the voltage instantly, I change the energy instantly.
Energy is infinite.
I cannot just move in 0 time the energy.
Yeah.
So I cannot have a voltage which is square, which is in a step.
You can't have energy which derivative is infinite.
Exactly. But you see, here, if I have the voltage which changes as a step, I would have
0.
a derivative. No, derivative here would be infinite. Okay. If the mathematician hears me saying the derivative is infinite, they are gonna kill me, because the derivative is the limit of the ratio, blah blah. If it exists and it's finite, okay, it cannot be infinite. They say, it cannot be. There is no derivative there because that cannot be infinite derivative. So if they hear listening the infinite derivative, they say, no, it's not. There's not infinite derivative or so. Whatever, who cares? We say we are engineers, we love very much the mathematicians, but we don't care much about them. So we cannot, we say infinite derivative, even if it's technically is not correct, but we don't care that much. So if we have, so this is the disclaimer to say that even if I say something technically wrong, I don't care too much about that. So if you have a step of voltage, you would have an infinite derivative. So it means that the current would be infinite. Because only if you have infinite current, you are able to transfer it in 0 time that charge into the capacitor. And you say, that's the best way to blow up something. Yes, if you have a capacitor and you connect it directly to a generator of voltage, okay, so let's say that you have a generator of voltage. And you connect it straight to the capacitor, that's not gonna be very nice. Why? Because let's say that there is no resistance whatsoever in the circuit, okay? Which is not true, of course. But you would have an infinite current going there, which is not something very large. You have a large current which can cause any sort of troubles. As a matter of fact, there are some resistances. The capacitor has always some equivalent series resistance, okay? So you have some equivalent series resistor. And the source of voltage also will have some resistance.
Yeah.
Because there is no source of voltage which can provide infinite current. There is always some limit to the current that can provide. So you always have some internal resistance. It might be small, but whatever. You always have this resistance. So, of course, in these conditions, the current will be limited by these resistances.
Which are tiny.
But still, it's going to be large current if these resistances are low. So the best way you can do to capacitor is connect it straight to a source of very high, to a source of voltage with very high current, so which is able to provide very large current, okay?
And also instantly discharging it with like a short.
That's the same thing when you discharge it, of course. So let's maybe now talk about this transient, okay?
I'll take that.
Yeah, you take this. So let's now talk about the transient to see if we can better understand what's going on. Oh, we have already studied the transient of the capacitor together, if you remember. Remember? It's already forgot. Yes, there is videos about that.
Oh, yes, in the integrator and derivative circuit.
Probably. I don't remember when we...
I don't know where
I remember when that we did it, okay? So let's see what happens if we have a source of voltage, let's call it Vs, and a resistor, R, which is whatever. We put the resistor intentionally because we don't want to close a circuit and having large current. Okay?
Limit the current.
So we limit the current. We have here our switch, which is gonna close, and it's gonna charge the capacitor. Okay. So let's write down always the equations, just to know that
what's what?
We have there the relationship for the capacitor. So do you remember? So the current is equal to what? Remember the physics. What happens when you put some current in the capacitor?
Charges.
And then the voltage?
My bad.
Okay. So remember, if you put some current, the voltage increases, which means that you have a change of voltage, in this case positive change, which means positive derivative and vice versa. Okay?
And just to recall,
So the capacitance is the charge divided by, so how much charge you get for 1 volt of voltage that you get on there, okay?
And then
1/2 CV squared. No. CV squared.
yeah, because there was a C there and that was squared and it cancelled.
Now, one thing to remember, so always watch where there is the derivative. So when you have the derivative, it means that it cannot
have a step response.
have a step, okay? So the voltage is not going to have a step response. The current, no problem whatsoever. It can change. There's no problem whatsoever.
It can be instantaneous change, but it will be limited by these.
We arrive to there. So what happens when I close this circuit? Let's say that
it's going to start charging.
The voltage of the capacitor
V naught is equal to 0.
At time equal to 0 is going to be 0, okay?
Yes.
So it's discharged. So when you close the circuit, here you have VC, which is 0, VS, and VR, okay?
Yes.
So VR is going to be?
Shouldn't we... okay, VR is going to be VS multiplied by R over...
Kirchhoff. VS.
That's what you want. VS minus VC.
Okay.
Sorry, I was going to do a voltage divider equation.
No. So you have VS minus VC, okay?
Yes.
Now, at time 0, so for time equal to 0.
Oh, VC is 0.
VC is equal to 0. So VR
equals
equal
VS.
to VS.
Yes, okay.
Sorry, VS, not VA2.
Yeah.
But VR is also the resistance and the current. So if I have a current,
Oh yeah, so now we can describe the current as IR. Okay,
so
yeah.
the voltage on the resistor is the current times the resistor, Vs, okay?
Okay.
So the current will be,
Vs over R.
okay.
Yes.
So this means that when we start our
Transient.
transient, the current instantaneously moves from 0 because before, for time lower than 0, before the switch was open, so the current
Was 0.
is 0. For time equal to 0, the switch closes, and the current will be Vs divided by R. Okay? So the current does change from 0 to boom.
Yeah, but that's because R doesn't have a derivative in it.
Because?
R, the resistor, has no derivative. It's
Why should that be a derivative?
well, because you said if there's a derivative.
Oh,
there's
yeah, but
no
in that,
step.
the derivative is going to be either on the current or the voltage.
Yeah, but because this is a resistor, you can have an instantaneous change.
I don't really think it's a matter of resistor. The resistor is not going to have a derivative, anyhow.
Yeah, yeah. So that's why.
Yeah, but it's physically, from the physical point of view, doesn't even make much sense to talk about derivative of the resistance. Unless you have the change of the resistance for the current, which can be given, I don't know, by other effort, like heating up. Okay, so you put some current, you warm up, so it changes. So you have a derivative, you change given by the current, but okay, that's not the point.
Don't worry,
okay?
don't worry.
Okay, so you go instantaneously from 0 to Vs divided by R, okay? So this is time, and this is current. Fine. Okay, and the voltage of the capacitor was 0. Maybe I should use other color, okay? The voltage was 0, and it keeps 0, okay?
Yeah.
Because it cannot change instantaneously. Then the current starts circulating. It will create some charge here, which means that the voltage
is going to increase.
Because, again, let's watch our equation. If you have a positive current, it means that we have a positive derivative of voltage, which means that the voltage is 0 here, but it has a positive derivative, which means that goes up, okay? Because the derivative of the voltage
is positive.
Is positive, okay? Then?
But it does not go up linearly.
Why? Because then, if the voltage here increases, VR decreases. Because remember that...
Isn't it IR decreases?
Sorry?
As VC increases, IR decreases.
The current decreases, but also exactly. So if this voltage increases, you have less VR. Okay, so let's say that this one goes up. It means that VR goes down. Okay, because as the voltage on the capacitor increases, it will eat up space for
the resistor.
The resistance. Okay. So if you have 5 volts, let's say, 5 volts here and 0 volts here, all the 5 volts will be there.
Yeah,
but as
you can, it might be wrong, but you can also think of the capacitor as a variable resistor, and at 0, the resistance
variable resistor. Yeah, if you really want to blow up your mind.
As it starts charging up, the resistance
increases.
Oh my God!
Yeah, okay.
And then that voltage divider
but
also.
But you know, if you say that, it's going to
probably mess someone else up.
Yes, very much. I think. Yeah. So I understand what you want to say, but it's really risking to mess up
the analogy.
No,
Not
people minds. It's like variable resistance. What the hell? Okay, but what I'm gonna say here. Let's say that you have at the beginning here you have 0,
Yes.
5 volts, 5 volts,
Yes,
fine.
yes.
Then there is some current. This becomes
1.
1.
Yeah.
And this becomes
4.
4. This becomes 2. This becomes 3, and so on. So it's gonna eat up. So it means that the current, as the current flows, the current will create a voltage, increase the voltage on the capacitor, and automatically decrease the voltage on the resistance. But you know that the voltage on the resistance is also equal to the current times the resistance. So if you have the voltage on the capacitor which goes up, it implies that the voltage on the resistor goes down because it will eat up the available voltage, taking a bigger share. So the voltage on the resistor will decrease, which means that the current also will decrease, okay?
Yeah.
Okay?
Yeah.
Does it sound okay? So it will decrease like this, okay?
Yes.
But remember, the current is the derivative of the voltage, okay? So if the current goes down, it means that the derivative of the voltage goes down.
Yes.
Which means that the voltage will continue to increase, but with a lower derivative, okay?
Yeah, the derivative slope will change.
Exactly. So here you have...
Or the value of the derivative will change. The slope is the derivative.
Yeah, so here you have a bigger derivative.
Yes.
So, big derivative of voltage.
Yeah.
Because you have a big current, okay? Maybe if you move, because I think... Okay. So here you have a big derivative of voltage because you have a big current. Then, as the current goes down,
the slope changes.
The slope changes. So when you arrive here, you have a small current. Therefore, here you have a small derivative of voltage because you have a small current, okay? Can we see?
Yeah.
Okay. Yes.
Yeah, everything's there.
And that's until then you arrive after infinite time.
Derivative is 0.
Derivative is 0, and that means that the voltage doesn't change anymore, okay? Then if you want, you can write down the equation, calculate the differential equation, and you find out that here the current will be this maximum value times e to minus t
RC.
tau. Tau is RC, okay?
Yes. I'll be honest with you, I haven't revised differential equations.
That's not a problem. I think it's at this level is pretty much intuitive. Okay?
Yeah, you just remember the
effect. What happens? It happens that you give some current, you know that the current charges up the capacitor, therefore this capacitor eats up voltage available for the resistance, so the current will drop because the current will be R times the...
Yes. Yeah, it's a first order differential equation. If
yes,
you have a second reactive component, then it's...
Then if you want a second order, like LC, you really need to go into those to see when it oscillates, when not.
Yeah,
it's not so intuitive anymore, so you should really go into mathematics.
Yes.
But at least for the first level, for the first order transient, you can see it physically what happens. So you see that here you have a current which at the beginning is very large, and it's allowed because it's current. So you can have a step of current in a capacitor. This determines how fast the voltage changes. The voltage starts from 0, cannot have a step, okay? Because otherwise it would be infinite energy, blah, blah, blah. But the amplitude of the current determines how fast is the rate of change of the voltage, okay?
Where does the E come from? Was it like...
because you have to solve the
differential equation.
And, well, okay, you have, look, I times R, okay? And that I is the derivative of the voltage on the capacitor. So if you watch this Kirchhoff law, you have voltage here is equal to resistance times I of the capacitor, okay?
Yeah, yes.
You have the derivative of the voltage plus the voltage. So you have something times the derivative of a function plus that function equal something, okay?
Yeah,
and then
that's where it comes from.
So if you have the derivative of a function plus something, it's going to be an exponential somewhere there.
Yeah, that's the beginning.
That's probably the worst explanation ever. I
saw it.
Okay, fine.
Yeah. Because basically it's going to be...
Derivative of a function is still the same of the same function. Let's see this RC, okay? Okay, if you solve the equation, you find out that this tau is RC. What is the physical meaning? Again, let's try to understand the physical meaning. This determines how fast this is evolving, okay? So bigger tau means that it takes more time to charge.
Yeah, it's the slope of the charge, let's say.
Well, if you take here, one tau.
Yeah.
If you take the slope here, you get 1 tau. So the bigger is tau, the bigger is time you need to charge.
Yeah.
But what does it mean from the physical point of view? Tau is given by RC, okay? Let me erase something here. And so, tau is RC. What happens if we change R, okay?
Tau increases or tau changes. Tau changes.
Let's say that R gets bigger. In this circuit, how is going to be the current if...
It will be limited.
Exactly. So if I have a bigger R, at the beginning of my transient, I will have Vs divided by R, this value, which is going to be the current, the initial current, let's say the current at time 0, is Vs divided by R. If I have a bigger R, the initial current is smaller.
Yes.
Which means that I have a smaller current, which means that I give less charge, so it takes me more time to build up the voltage that I want to take. So it will take longer to, if I have a smaller current, it will take longer to give all the necessary charge to build up
steady state,
the voltage that I get at the steady state, okay? So, if I have a smaller resistance, then the current
is greater,
will be larger. And if you think to the extreme, when you go to 0 resistance, you get exactly to the point where if the resistance goes to 0,
I goes to infinity.
I goes to infinity, which in fact is what we saw before. Without a resistance, you try to charge instantaneously so as you decrease the R,
tau decreases.
The current gets bigger and bigger because there is something less powerful in limiting. I'm limiting less and less the current. The current gets bigger, bigger, bigger until I try to go instantaneously to the voltage, to the final voltage, which means that, of course, I'm giving infinite resistance. Okay, so the role of R in tau is to say, okay, I determine how large is the current in the circuit which is gonna charge up the capacitor, and therefore how long it takes eventually to finish the charging process, because the smaller is the current, the more is the time necessary to arrive to the complete charge of the capacitor. What about C?
Well, C can also affect the time constant.
Of course, because C means that, remember, Q equal CV, okay? So we arrive always at the same final voltage, okay?
Yeah, Vs.
Because at the end, we still have Vs equal to Vc. That's the moment where these two voltages are the same, so there is no voltage on the resistance, therefore there is no current anymore. Okay? The only moment when the flow of current stops is when these two voltages, Vs and Vc, are the same, and therefore there is no reason for the current to flow, because there is an equilibrium. So eventually you arrive always at Vs, okay? But if you have a bigger capacitance, you have bigger charge.
Yeah.
So you need more current. So
yes.
For a given current, let's say that now we set resistance, we don't change it anymore.
Yeah.
So the current will be over Vs divided by R. So for that given current, determined by Vs and R, if I have a bigger capacitance, I have to give bigger charge to build up the same voltage. Okay?
Yes.
So that's why these two values, R and C, are together determining tau. So in both cases, if I have bigger R and bigger C, I get a bigger time to finish my transient. Okay? Now, what happens? Is that clear?
Yeah.
Okay. Now, let's say that we charge our capacitor. Okay, so let's say that we arrive to the point where the transient is over. Okay, we charge completely our capacitor. So we have a current at some point, which is finally arrived down to 0, and the voltage, which was
now it's
built
Vs.
up and arrived to Vs. Okay, this is the voltage. This is time. So the current eventually arrived to 0 when we finished our transient, and the voltage arrived to Vs.
Yes.
Now, what happens if I discharge the capacitor? Let's say that now our capacitor, I don't have much space here.
Just remove the source.
Okay. I have my capacitor here, and I connect it to another resistor, okay? Let's call it R2, just to change the name. Could be any resistor. Doesn't need to be the resistor we used to limit the current at the beginning, okay? Could be any resistor. One load, we charge some energy in the capacitor, and we want to discharge it on another load or whatever, okay?
Okay.
So, now, what happens to the voltage and the current? You have the voltage, which has been created by the previous process of charging.
It's charged.
And then you apply it to a resistor. So you have a current, which is going to be, if you have a voltage and the resistor,
V over R.
Exactly. So the voltage of the capacitor divided by the current. Now, let's be careful to the sign of the current, because we considered previously the current positive with this sign. But now that I build up the voltage and I connect a load, the current will go to the load, okay? So maybe I should redraw this. So the current was positive and it went inside.
Yes.
Okay? And at some point it arrived to 0, okay? Then at time equal to 0, I connect the capacitor to the resistor, okay, and the current goes out. So
instantaneous.
It starts from here, and the value of here is Vs divided by R2.
Negative.
Negative. Because Vs is the final value that we arrived here.
Yes, yes, yes.
And then
It's going to have an exponential decrease towards 0.
Okay. And
Vs
the voltage
will have an exponential decrease.
you remember that the voltage is the integral of the current. So if I take out charges, the voltage goes down. So it will go down to 0. Okay. Again, the voltage cannot change instantaneously.
Yep. Because it's defined by R.
But the current can. Okay.
It's limited by R.
It's limited by the it's limited by the yes, by R, but it's limited by the fact that
it's a derivative.
It's the derivative. So, of course, if I take smaller r, okay, if I take smaller r, the current will be larger.
Yeah.
And therefore, it will discharge faster to 0. But of course, larger current can screw up everything. So the same thing that it's not a very nice idea to go there and on the big capacitors with a lot of charge inside and put there or there are some crazy guys who measure the voltage using the tongue. You know, they take the batteries, with the tongue, and say, I feel some fuzz here. It means that there is charged up. And say, no, don't do it. Not a good idea.
But a battery's current is limited, where a
but
current is not.
If you're crazy enough, you can do it. Well, when I was a kid, I've done many crazy things. Thanks God, I'm still alive.
Yeah.
But the point is that if you're working, when you're working around on some circuit, you're probing and so on. By accident, you might short some capacitor when you're working, and it could lead to large current. So when you have some very, very large capacitor in your circuit, it's always a good thing before start probing around to put there some resistor, discharge them. If you measure that there is some voltage, it's a larger capacitor, and you see that, okay, maybe it's a large charge inside there, just discharge them first and then start probing around.
That's why there's also bleed resistors on the power capacitors. So when you turn it off,
you can, of course, then when these things becomes more and more important, they try always to give you the ways to do it safely and not just to search around some random capacitors. Because the point is that very often people tend to forget these things. Yeah. And then there's huge.
Especially if you have a ESR, not an ESR, an LCR meter, and the capacitor's charged with a greater voltage than what the device.
So don't forget that.
Always discharge a cap. And a capacitor has an ESR, but it also has a parallel.
It has also an inductance.
Yeah. And capacitors, you have radial capacitors and axial capacitors. Axial capacitors have more operational inductance than radial capacitors because it's almost like a wire, where a radial capacitor has an input and an output. So those inductances.
I'm really not confident with this. I just remember that according to the packages, you have different values of inductors. I think the at least for SMDs, the bigger is the package for a given value of capacitance. Bigger is the package, the bigger is the inductance. I'm not sure.
But those have tiny inductances because obviously they're small.
Well, of course, the inductance is always there. As soon as you have a wire, and there's some current, it means that it closes somewhere. So you're gonna have some inductance.
But obviously at very high frequencies.
It gets handy. It starts having this effect high.
I was talking about this. You can have a capacitor that has an axial thing, so it would look like that.
What do you mean by axial? I don't.
The leads are axial, so it goes out on the axis, and then you can have a radial. I think these are the words: a radial capacitor like this, where the leads come out like that.
Okay.
This
one has what you meant.
More inductance, and this one has less inductance because those.
I understand what you meant. Okay. Okay, I understand what you meant. Yeah.
But I like these capacitors more because they don't take up so much space.
Ah, okay, well,
You know what I mean?
that's the least important thing when it comes to...
Ah, no, the circuit boards need to look nice too.